I thank the Didactics division of the Italian Chemical Society for inviting me to talk to you today. I've been asked to talk about issues relating to the teaching and learning of chemical bonding, and I'm very happy to do that, as this has long been a topic of special interest to me. What I hope to show you is that although research has found a wide range of alternative conceptions in this area, there's a pattern that links some of the most common and significant conceptions that students tend to form. I hope you'll excuse me if I do not go into details of the individual studies I draw upon, which are reported in published sources. The respondents are secondary age learners, but some of the findings have been reflected in studies carried out with university students. I will begin by offering some background, by briefly considering what we mean by alternative conceptions and how a constructivist perspective on learning views the development of such conceptions. Much research has characterised and catalogued student thinking about a wide range of science topics at different educational levels, from young children to postgraduates. A key finding is that we cannot assume that student understanding falls on a straight line between ignorance and canonical knowledge, as we find that often students have ideas, sometimes vague but sometimes well considered, that are alternative, quite different from the canonical knowledge. In practice, in any class, in any science topic, a teacher is likely to be working with students who hold a wide range of different ideas about that topic. There are often clusters of similar ideas and some very common conceptions, but there will be variations in how different students understand and apply their ideas. This is certainly the case with chemical bonding, where there are some strong commonalities shared by many learners, but even then, also fine variations between students. Alternative conceptions have a wide range of different sources. Some reflect spontaneous making sense of natural phenomena, but social processes are also important, including teaching, of course. Research suggests that learning is interpretive, incremental, and iterative. It is interpretive as we use our existing fund of knowledge, beliefs, ideas, and experiences as a resource for interpreting experience. Learning is incremental as there are limitations to the processing capacity of human beings, in particular in terms of working memory and forming long-term memories. So learning needs to occur in modest learning quanta. Given that learning is interpretive and incremental, it's inevitably iterative in the sense that the ways we are thinking now tend to shape new learning and so future thinking. That doesn't mean we cannot change our minds, but radical conceptual change is a lot more difficult to achieve than modest accretion to our existing ways of thinking. If learning requires interpretation, then teaching is about making the unfamiliar familiar. And teachers draw upon a wide range of tactics to show how what is unfamiliar to students can be understood, at least as a starting point, in terms of what is already familiar. This can include demonstrations, simulations, models, anecdotes, narratives, and a wide range of comparisons with everyday life and cultural references. Interpretation during learning includes a good deal of making sense of metaphor and simile, and understanding the unfamiliar by noticing analogies to the familiar. And as learning is an iterative process, the question of the origins of alternative conceptions may not be straightforward. Often these have evolved from multiple sources. That was something that Vygotsky recognised in his theory of conceptual development, describing how spontaneous and formal learning interact to give what we might call melded conceptions. Vygotsky wrote about how spontaneous conceptions and academic concepts that were met in formal education interacted. Learning formal concepts provides a language for talking about and thinking about spontaneous concepts deriving from tacit knowledge not readily available to introspection. Pre-existing spontaneous concepts provide the basis for making sense of formally taught concepts and relating them to personal experience. In practice, this may be indirect, in that we often understand more advanced abstract conceptions in terms of previously learned abstract concepts, even if those are ultimately, if indirectly, grounded in spontaneously formed knowledge based directly on experience. That is, once we've developed abstract concepts based on direct experience of the world, and these abstractions have become consolidated as part of our way of thinking about the world, then these abstractions can themselves be the familiar ground on which new learning can build. I suspect that for most delegates attending this meeting, there is a sense in which such abstractions as methane molecules and hydrogen bonds are as real as conical flasks, Bunsen burners, or even laboratory stools. With sufficient familiarity and use, the most abstract ideas become part of our reality, whether that is an anti-bonding orbital, phlogiston, caloric, or even the desire of atoms for full valence shells. Vygotsky's account used the image of spontaneous and taught concepts moving or growing toward each other, but I've here reimagined this as a kind of hybridization process or melding. Like a compound, a melded concept is something new, not simply the aggregate of its component elements. Given the complex origins of many student conceptions, it's not surprising that they vary in terms other than just their match with canonical science. Some of the main dimensions are represented here. People will form some conceptions that they entertain for just a short time, but then readily discard, as well as conceptions that they become highly committed to. People form odd, isolated ideas, as well as conceptions that become highly linked into extensive networks or frameworks of conceptions. Sometimes a person may have available manifold conceptions of the same target that they can switch between. Being able to build up a new way of thinking that's inconsistent with an existing mode is only problematic if we want to commit to and believe both alternatives. And this potential for multiplicity allows a new way of thinking to be explored over time without first having to commit to it and dismiss our previous ideas. Research also shows that people develop many implicit patterns of thought, which can channel their conscious thinking without them being aware of the source. This is something like intuition. Dissessa has explored many of these implicit knowledge elements, especially in relation to physics learning, that he calls P-prims for nomological primitives. The chemist and philosopher Michael Polanyi had long ago recognised the importance of tacit knowledge in scientific work. These different characteristics relate to how readily a person may shift away from a particular conceptualization. Once we move beyond assuming that knowledge can be transferred directly from one person to another, and accept that the knower comes to construct an understanding by interpreting, for example, teaching, based on an existing fund of interpretive resources, existing knowledge and understanding, past experience, word meanings, and so forth, then we need to understand teaching as a component of a system where the particular learner is as intrinsic to that system as the particular teacher. For effective teaching, the teacher needs a good model of the learner's state of readiness for learning, to know about their particular fund of interpretive resources. That is, teaching is based on assumptions about what a person already knows and understands, and how they will interpret teaching. There is much scope for the teacher's model of the learner and how teaching will be understood to go wrong. The teacher may assume knowledge or understanding that is not present, as the learner does not have the prerequisite knowledge. The teacher may assume teaching will be interpreted in terms of existing knowledge or understanding that the learner actually has available, but which is simply not activated and brought to mind in the context of the teaching. Links that are so obvious to the teacher that they seem self-evident may not be obvious at all to the learner. Also, the fund of interpretive resources a student does have available and may activate may include ideas which are contrary to science, alternative conceptions and unhelpful intuitions. The student's fund of interpretive resources will also include many features which are canonical in their own terms and contexts, but can be inappropriately applied outside their usual range of application. For example, drawing analogies that are unhelpful in relation to the ideas being presented in teaching. In one study, students were asked about the nature of the force attracting an electron to the nucleus. A naive expectation might be that most would know it was obviously electrical, but there may be some students who didn't know and so could not suggest a response. In practice, a diversity of answers was offered, half of which were clearly incorrect and more than half of the rest were considered vague. In this sample at least, the most common response was that the force was gravitational. In chemistry, learning of key concepts and ideas is made more difficult by the way chemists take everyday phenomena, such as burning, and redescribe them both in terms of theoretical chemical concepts and also for explanatory models in terms of structure and processes at a scale far beyond human observation and experience. We tell students that chemistry is all around us, but actually we do not usually discuss the common materials of everyday life, air, seawater, orange juice, wood, and so forth, but largely restricts school and even university chemistry to properties and reactions of samples of pure substances, most of which are seldom found anywhere outside of chemistry labs. Materials are more complex, and materials science is another discipline. Chemistry is a science of special cases. In that sense, chemistry is already highly abstract, even before we mention molecules and the like. In school, learners are told about molecules and ions and electrons and bonds and ligands and delocalization and electron spin and orbitals and spin pairing and quantum numbers and all the rest. In more advanced courses, such abstract notions are developed and linked to new abstractions: anti-aromaticity, paramagnetism, chemical shift, and so forth. Chemists teach that familiar phenomena, as redescribed in terms of chemical concepts such as oxidation and neutralization and so forth, emerge from the interactions of these conjectured submicroscopic species. Species which do not have the decency to behave as either familiar particles or waves, but rather as strange hybrids. So electrons have spin without spinning. Atoms are tiny, but mathematically extend to infinity. Orbitals form into shells, but actually interpenetrate each other. Electrons can never be pinned down and are best understood as smeared out into clouds or density patterns. And molecules and ions are usually treated like particles, but have neither surfaces nor definitive volumes. It's no wonder so many students struggle to make sense of this unfamiliar zoo of non-observable ghost-like entities that give rise to the very real phenomena that we see in the chemistry laboratory. Chemical bonding is of course a topic that is inherently about these quanticles, these non-observable entities that behave quite unlike objects that learners are actually familiar with. Students meet no end of representations of atoms and molecules, ions and more complex structures, but none of these various representations are realistic. By its very nature, a chemical bond is not the kind of thing we can represent realistically, any more than we can realistically represent love or justice in material form. Indeed, it's often suggested that the term chemical bond suggests an object, when we should be teaching about a process, chemical bonding. No doubt, the challenge of representing in simple visual forms what is not, in the normal sense, material, contributes to some common alternative conceptions. Here are two classic misconceptions. Substances with covalent bonds often melt readily, and salts do not. So the ionic bond is assumed to be generally stronger than the covalent bond. There's nothing wrong with the logic per se, but often learners are taught about covalent and ionic bonding without any mention of intermolecular forces till much later. Bonds, often imagined as something material like a spring or a stick, are sometimes said to contain energy that is released when they break. Despite chemistry teachers being well aware of this problem, it's still possible to find biology or biochemistry books that refer to the energy-rich phosphate bonds, and even imply that breaking these bonds releases energy. As teachers, we may not appreciate how students who seem to have learned our abstract concepts may still be struggling to overcome a more material idea of bonds, and to make sense of our representational formalisms. An example might be the students who saw the ring used to represent an aromatic system as signifying a place where the spare electrons were located. For these students, in benzene, this representation shows each carbon centre has 3 bonds, and given the valency of 4, that leaves an electron not involved in bonding, which is spare, and can be stored in the ring, which, as shown, is inside the molecule. The colours here are nothing more than an accounting device to help keep track of the number of valency electrons. Yet often, for learners, any electron belongs to a particular atom. As one student once told me, it would be odd if on bond breaking and the electron did not go back to its own atom. It is as if each electron has a natural place or a home base and behaves like an undergraduate who naturally returns to the family home when the term breaks up. Today, I mainly want to focus on a group of common conceptions, such as those listed on this slide. There is something of a range here, but my argument is that these are not simply unrelated conceptions, but rather commonly part of a coherent and in its own way quite logical conceptual framework. I would also suggest that this common alternative conceptual framework must, at least in part, derive from chemistry teaching. I've pointed out that many conceptions have convoluted origins, and I am sure there are some intuitive ideas at work here. The idea that electrons have a natural place in their own atom might seem to reflect this, as does the idea that full shells have some special inherent status, simply because of their fullness or symmetry. But no one spontaneously develops a way of thinking about chemistry in terms of atoms and molecules without being taught about the subject. Some of the ways we teach the subject must surely, if not encourage students' alternative conceptions, then at least offer fertile ground in which these alternative conceptions can grow. From interviews, I identified 3 related conceptions that seem to commonly be developed by students when taught about ionic structures. Firstly, just as a valency of 1 restricts an atom to form 1 covalent bond, learners often assume the electrovalency limits the number of ionic bonds formed. So in sodium chloride, each Na plus can be involved in 1 ionic bond, each Cl minus can be involved in 1 ionic bond. Of course, that makes little sense if we see the bonding as the balancing of the attractions and repulsions between different charges. But usually students do not see the bond that way, even though it's based on a simple idea they should have learnt in physics that opposite charges attract. Rather, a bond is seen to only exist where an electron transfer event has taken place. Only a sodium ion and a chloride ion that have shared this intimate act of being formed from atoms where one donated an electron and the other one accepted it are bonded. Indeed, this is almost understood as a good marriage rather than some casual coupling, that history will bind those ions forevermore. When I talked to one student about precipitation reactions, it became clear that divorce was possible and needed to occur before a new partnership could be formed. So if you produce lead iodide from solutions of lead nitrate and potassium iodide, some of your students may actually think the iodide ion in solution returns an electron to potassium before accepting a new one from lead. Given that bonds only form where there is this history of electron transfer, then the solid ionic structure must contain different kinds of interactions. Ionic bonds, and then just forces between other adjacent pairs of oppositely charged ions. This scheme is much more complex and convoluted than the scientific model, but seems to make more sense for many students. This has been demonstrated in more than one national context. I've highlighted responses where most of the students agreed with statements which reflect the alternative conceptions. Even when these statements were not thought true by a majority, they still found substantive minority support. Most students accept that only one ionic bond can be formed by an atom of sodium or chlorine. Most students think the interactions in the lattice comprise two different categories of interaction: ionic bonds, supplemented by forces due to electrical charges. Most students recognise ion pairs as distinct molecules within the lattice. Students asked to look at a slice through an NaCl structure may actually confidently suggest which pair of ions in the lattice are actually bonded and which not. And as many of you will be only too aware, the molecule-like NaCl units are often assumed to exist in molten or dissolved sodium chloride, something which makes good sense in terms of the alternative model so many students develop. Of course, this model does not explain the high melting temperature of sodium chloride, or why it conducts electricity in solution or molten. That said, this model can explain why sodium chloride dissolves readily in water, as the strong ionic bond does not need to be disrupted, only the forces between molecules. At introductory level, the interactions that allow solvation are seldom discussed in any detail, and students aware of them do not consider them chemical bonding. I suspect that the popularity of images such as this in textbooks and on websites influences student thinking. In the case of sodium chloride, this shows a process between atoms that are very unlikely to be present with a significant abundance in reactants. It is also a process that is not viable, as the energy available from the electron affinity of chlorine is insufficient to provide the ionization enthalpy of sodium. However, This is often presented as a model of the formation of ions and so of the ionic bond. It is scientifically incorrect, but it is simple enough to easily be represented in textbooks and in classroom images. I consider this cluster of alternative conceptions to comprise a framework, as they are mutually self-supporting and offer a coherent account. This diagram also links to two of the most powerful aspects of a broader, common alternative framework I'm drawing your attention to. These are the assumption of initial atomicity and the full outer shell explanatory principle. The assumption of initial atomicity is the tendency of people to think about chemical processes, such as chemical reactions, in terms of atoms interacting. Yet, in doing chemistry, we usually start with substances that are molecular or ionic or metallic. Psychologically, atoms seem to make sense as the building blocks of matter. I think there's an interesting question about the extent this derives from something inherent in the way we think, or is conditioned by the way the subject has tended to be presented and taught. I suspect the truth is a little of both, that we teach in a way that seems to work psychologically, and that reinforces that way of thinking as being natural. Nature itself, however, seldom favours atoms under the conditions we normally experience. And once we focus on atoms, then electronic configuration seems very salient. Students at introductory level, and even sometimes well beyond that, do not usually seem to understand, or at least describe bonding as a process that occurs due to physical forces, but rather a response to the needs of atoms. I am not sure how well this phenomenon is reflected in other languages, such as Italian, but even advanced English learners commonly talk as if atoms are sentient agents, being aware of their electronic configuration and actively seeking to change it through deliberately engaging in processes such as sharing or donating or accepting electrons. The full outer shell explanatory principle is of course closely related to the octet rule. The octet rule itself is very useful for beginners. The octet rule helps predict which molecules and ions are likely to be stable enough to be viable in chemical systems. It is those ions and molecules that are likely to be participating in chemical reactions discussed in elementary chemistry. Participating, that is, as components of either the products or reactants. The alternative conception promotes the heuristic to a principle that explains why reactions occur. It's only possible for it to be applied in this way when reactants are assumed not to be obeying the octet rule, usually because of the assumption of initial atomicity. Even as a heuristic, the octet rule is fairly limited. It soon runs into difficulty once we get into period 3, and has exceptions even when limited to considering the first two periods. With simple ions, it is a useful guide, as long as we are aware of the chemical systems that provide the context in which the ion is to be found. Ions in chemistry are usually stabilised by being part of a lattice or being solvated, and what applies in those chemical contexts does not apply to comparisons between isolated atoms and ions. Yet it is common for students to assume the sodium ion is more stable than a neutral atom. Even if we try to explain this by assuming learners are thinking of a suitable context where the ion is stabilised, we might struggle to explain why a highly charged sodium anion is considered more stable than the atom. The unlikely Na7- anion is often considered just as chemically stable as a familiar sodium cation. I imagine a context could be engineered where the Na7- ion would hold together, just as it's possible with sufficient investment and ingenuity to mimic conditions similar to those soon after the Big Bang. But such conditions, such extreme conditions, are not coming to a test tube near you anytime soon. To some extent, similar patterns are found with other species presented to students. Even with elements not known for being readily found as simple ions. Of course, in the case of period 3, a full outer shell is not the same thing as an octet. This perhaps explains why the chlorine 11- ion is considered by a substantial minority as being more stable than the chlorine atom. Again, this is not a species you're likely to find in any reagent that the technician is likely to be able to fetch from the stores. An objection could be made to these probes that they're not comparing like with like, as the system of an ion and an atom has a different set of constituents, a different number of electrons. Yet, for some students, the focus on the outer shell is such an imperative that it's assumed that an excited atom is more stable than a ground state atom when that allows the outer shell to have an octet. A majority of respondents thought that a sodium atom will spontaneously emit an electron to become an ion. Here we are, of course, discussing a process that is normally considered in terms of the energy input required to achieve the ionization. And here are sketches of the standard ionization energies for the elements in the periods 2 and 3. In each case, the most energy is needed to remove an electron from the octet of outer electrons in the valence shell of a noble gas. For many students, this is evidence of the special stability of the octet. Breaking up the octet or full shell requires more energy. Of course, that is not what these patterns suggest at all. We see a general upward trend across a period with the two familiar dips which are understood in terms of the type of orbital and the pairing of electrons within p orbitals. And if we adjust our ionization values for these factors, we can see a pattern that is more or less a linear change, as nuclear charge and so core charge increases across a period. That is, there is no evidence here of any special stability for the octet structure. Yet, despite commonly thinking that ions with octets will be inherently more stable than atoms, learners still take atoms as their starting point for explaining chemical processes. Here, learners were asked about why hydrogen and fluorine react. Respondents were offered a formula equation showing reactants were molecular, with representations of those molecules as well as atoms. A simplification of the reaction as a process involving just two reactant molecules might look like this. Yet most responses, even from students at what is called advanced level in England, tended to explain the reaction in terms of the atoms seeking to fill their shells. The process they are envisaging starts with atoms, not molecules, despite the equation provided. Perhaps we should not be surprised. It is very common for images used in textbooks and websites to represent chemical reactions as if the reactants are atomic. Even when the process actually starts with molecules. It is not even appropriate to assume that in such a reaction the molecules break up into atoms that rearrange. In practice, reactions often have very complex paths, with many molecules and ions being formed and interacting in a reaction mixture. Even in deep space, the tenuous matter found in the interstellar medium is not a low-pressure gas comprised just of atoms, but includes all sorts of ions, molecules, and radicals. Some of these have the decency to observe the octet rule, but others are impertinent enough to ignore it. If chemical reagents are assumed to be atomic, or to be readily atomized when reaction occurs, then the full outer shell explanatory principle can be applied as a basis for why reactions occur. And again, assuming we start with unbound atoms, why bonds form? Often in introductory chemistry, bonding will be discussed in terms of two bond types that we know can be considered to be extremes of a continuum, but are introduced as discrete types. Later, we need students to understand electronegativity and degrees of covalence and ionic behaviour. It is quite reasonable to start teaching a simple model and look for progression to something more nuanced and sophisticated. Often, however, when learners meet polar bonding, they do not consider it as intermediate between two ideal prototypes, but a subdivision of one category. We can understand this if covalent bonding is seen as atoms obtaining full shells by sharing electrons, and ionic bonding is understood as atoms achieving full shells through electron transfer. From this perspective, polar bonds can be understood as a kind of ionic bonding that has not gone to complete transfer, or more commonly, as a sharing of electrons between two unequal partners. This notion that bonding is either electron sharing or electron transfer has consequences for learning about other kinds of bonding. Some students do not think metals, being elements, need bonding, perhaps thinking in terms of elements as atomic. And where students have learned there is a sea of electrons, they may feel this is a sufficient explanation in itself, just as they often accept the term sharing as something more than just a metaphoric label. Whilst there are many variations and idiosyncrasies in student thinking, I believe there is a broad common alternative conceptual framework which encompasses many of the most tenacious alternative conceptions about bonding, including subsuming the molecular framework for ionic bonding. At the core of this framework is the idea that chemical processes are driven by the needs of atoms to get octets or full outer shells. This is something which may be encouraged by the way the subject is often presented in books and on websites and sometimes in our teaching. In particular, the strong focus on the atom encourages this way of thinking. The atom is a convenient and psychologically attractive building block for us to use in our teaching. But in nature, most common chemistry does not involve substances comprised of atoms. And those substances that commonly exist as atoms do not have much chemistry. Learners make sense of covalent and ionic bonds as atoms acquiring stable structures by sharing or transferring electrons. But this cannot readily be extended to explain metallic bonding or polar bonding or dative bonding or solvation or van der Waals forces and so forth. For many learners then, only covalent and ionic bonds are proper chemical bonds, and other types of bonding have to be understood as variations on these two types, with their narratives of helping atoms form octets. Else they are seen as just forces that are something less than bonds. For the chemist, chemical bonding may be a label for physical processes involving forces, but for many learners, the chemical bond is primarily a means for atoms to achieve octets or full outer shells. This way of thinking also leads to misunderstandings across other important topics such as ionization energy, equilibria, properties of salts, and so forth. In educational terms, we're not dealing with a range of isolated conceptions that need to be challenged in teaching, but rather with a coherent and integrated way of making sense of much chemistry. And as learning is interpretive, incremental, and iterative, once this way of thinking is established, it is used to try and make sense of subsequent teaching. It can be very hard for students to put aside this way of thinking once it has been adopted. Unlike misconceptions of force and motion in physics, or plant nutrition in biology, young children do not have many informal learning experiences of the nature and interactions of atoms, molecules, and ions in their everyday lives. There are surely intuitions at work that make atoms such attractive building blocks, and make octets and full shells seem inherently desirable and stable, and so a basis for explaining reactions, bonding, and so much more. But generally people first learn about the submicroscopic accounts of chemical structures and processes in their studies of chemistry. So I suspect that the way we teach this topic is a major contributor to the development of these ideas that seem to be adopted by so many students.